In the previous class, we started with NFS as an example of a networked file system. And again, just to recapitulate, with storage area networks, we assume that there is a single application which is managing the storage. So there is no, essentially you can say that there are no consistency problems. Somehow, somewhere in the application, they are managing issues relating to consistency, issues relating to quality of service, security, etc. So it's not part of the storage system to take care of it. It is the part of the some other upper layers, typically the application, to handle it. Whereas with once you go to NFS, the idea here is to provide some level of support in some of these areas. It could be in the case of consistency management, or it could be in terms of security, etc. Now, NFS version 2, when it came up, it was very early on, 1980s. So it is particularly simple in its ideas about how to handle these issues. So we'll see what are some of the problems. I mentioned some of this in the previous class, but I think I'll just reiterate one more time. For example, maintaining Unix semantics is not easy for NFSv2. Why is that? When you open file in Unix, right, what happens is that regular Unix checks on first access. Once you have access the first time, it's never checked again. Once you have a file descriptor, that's it. You no longer are subject to any checks. Whereas NFSv2, being a stateless protocol, essentially what happens is that if the permissions have changed, then it may be, essentially it gives different behavior than what POSIX gives you. Same thing with atomic IO operations. It's possible that while you are doing some long IO, let us say 4 megabytes or whatever, since it takes multiple times and multiple network packets to go back and forth, some things can change on the server. So that means you cannot give atomicity guarantees. Similarly, there is an issue of what is called deletion of open files. This is a standard way in which temporary files are created, and then to make sure that you don't forget to delete them, what happens is you open a file and delete them. And the idea here is that in POSIX, what it happens is that the open file is essentially still available for reading and writing, whereas once the particular temporary file is closed, then the file blocks are returned back completely. Okay. Now, this semantics in POSIX also has some problems in being supported in NFSv2. For example, if the server itself deletes a file, then basically, as we discussed previously, every new time an inode is reused, the generation number increases. Because of that, it turns out that if the client now goes and asks for the same file, the open file, essentially it's going to get a different, let's say, generation number, and therefore it will come back and say that's a stale file. Okay. So you can't really have essentially the kind of idiom that is there in POSIX of deleting an open file. Okay. So for that, you need to do some other things. For example, in the case of some of these things, there is some checks possible, solutions possible. Let's just take the case of deletion open files. Suppose there's a client and one of its processes has opened a file, and some other process on that same client deletes it. Then since the client, actually all the requests have to go to the client can keep track of such things coming from various processes in that particular client, and in case somebody has deleted a file, an open file, it can actually know that this is what has happened, and then therefore it can essentially still provide POSIX kind of guarantees by renaming that file to some name which cannot be guessed by anybody else, and accessibly making that particular file still available to the party who has got the open file still. Whereas, but this solution doesn't work in case the server deletes the file. So there are some holes in the way NFSv2 can handle some of this POSIX kind of semantics. Okay. Now, similarly, there are some problems with cache consistency guarantees, and basically NFSv2 checks if the modified time of a client of the cache data different from server modification time. Okay. If by this way it can figure out if something has changed, but if this works only if the server is making changes. If some other client is making changes, this doesn't work. Okay. Essentially, the client has some modified time, and there is a different time which, if it is informed, then it can figure out if something has changed. But if multiple clients are modifying it, they may not necessarily inform the server. Therefore, across multiple clients, this may not work. So in a sense, your cache consistency guarantees are quite weak. Again, with respect to security, there are various models. Again, when NFSv2 came on the scene first, there was no serious use of cryptography. For example, public key encryptor systems came out only in about approximately 1977 or so. By the time various methods worked out, it was rather, let us say, only the next one decade. So security that NFSv2 provides is closer to the standard Unix model, where it's assumed that across all the clients, there is uniform Unix-like UID and GID, user IDs and GIDs, and therefore, that's a model that has been initially proposed, and this turns out to be somewhat problematic on larger installations, especially when administration is handled by multiple parties. And similarly, the data traffic itself goes on unsecured networks. There is no notion of encrypting the traffic that is being sent out in form of requests or the data that comes in. Again, the reason why that has happened is because NFSv2 came much earlier before security became important in local area networks or on internet, and therefore later models attempt to handle this part of it. Okay. You can see the kind of problems that are there in this area. For example, a root on one machine could be, let us say, should not be allowed to act like root on some other machine. Okay. If that is allowed, then any user whose root on a particular machine essentially has complete control of the whole of the network. So which is a problem, and therefore there are some elementary methods available in NFSv2 to take care of these kind of problems. What they do is, if somebody says your root, they are mapped to a nobody. That means that even if you claim to be root, the minute the request comes with a root as this one, it is mapped to a nobody on the server side. So there are some elementary methods, but that's certainly not very satisfactory. Similarly, performance problems are also serious in NFSv2. For example, you can have UDP storms. Again, NFSv2, when it first came about, they initially proposed that UDP be the choice of protocol. The reason being, when the early 1980s, when these protocols were defined, TCP was considered too heavy. It was taking too much processing in the CPU. Therefore, UDP, which was less of a issue with respect to processing, actually hardly does any processing. Therefore, it was considered to be a better way to get effective throughput in the system. Now, with UDP, you don't have any flow control of any kind. Therefore, it can turn out that you can have UDP storms. Okay. So, with that, the NFS, let us say, server can get overloaded. Once it gets overloaded, it looks as though it has crashed, and all kinds of problems start cropping up. Okay. Similarly, because of one critical issue about NFS being that the server being stateless, any writes that have to be sent to the server are synchronous. Now, once you have synchronous writes, it turns out to be make the server very slow in terms of requests. For example, if you have a disk as your device for synchronous writes, essentially you have about, in those days, about 25 milliseconds per write. That means you could at the most have 40 IOPS per second. You could not go beyond 40 IOPS per second, or something equivalent, somewhere about 40 to 50. So, to handle this problem, there were various ad hoc optimizations that had to be devised. One of them was to have, let's say, non-volatile memory of some form, and usually that involved non-volatile, essentially memory with battery backed up, which is battery backed up, and various other kinds of models. Okay. Another issue about NFSv2 is that it requires a lot of other infrastructure, something called Portmapper, mount daemon, log daemon, stat daemon, etc. Okay. Let's go in the reverse order. Stat daemon basically is some way of notification when some machines have failed. Sometimes you have to do some elementary, you need to know which machines are up and down, and stat D is something that is required. This is not part of the NFS protocol. So this also had to be taken care of. But your NFS system itself needed to access this information. That means it had to go through some other protocols outside of it. Similarly, log daemon. Now, when you have multiple users updating a particular file system, you need to have some notion of, let us say, who owns the file for the time being while it is being updated. If you have concurrent writes to the same file, it's possible that you don't get any consistent version of the view of the file. So you need a log daemon, and this log daemon by definition had to be stateful. Because it had to be stateful, it could not be fit into the NFSv2 model. Okay. Because NFSv2 essentially says that the server is going to be stateless, it is not going to keep track of logs it has been given to various various clients. So this log daemon again sits uncomfortably with the rest of the infrastructure. Okay. There's also another protocol called Mount-D, which basically helps you to figure out which file systems are available out there and which can be mounted. And again, this is outside of the NFS protocol. Okay. And typically these are done through some user level daemons, somewhat different from the way the file system model is there in NFSv, which is typically kernel solutions, kernel based models. Similarly, this Portmapper also was another issue that has came up. Basically, there were no standard ways in which RPC calls could be mapped to services. So there had to be some way of mapping any particular service you needed to some particular port numbers, and these port numbers were not specified in NFSv2 protocol. Okay. Essentially, when NFSv2 came up, networking was still in its infancy, so not many things were defined. So it was expected that some other models will be used to figure out all these things. For example, if you had to have this mount daemon or log daemon, they will be listening on some ports. The question is, how does the NFSv2 protocol know where these guys are listening on? So this Portmapper had to come into the picture. Okay. So this also in the beginning was sort of semi-okay, but later it became complicated because it turned out that these Portmapper, Mount-D, log-D, stat-D, etc., they can get into problems with once you have firewall. Again, the security issue of local area networks was not very clear in the very beginning. So once you cross local area networks, then it turns out that there could be firewalls involved, and they might block these ports, and the ports that were initially used were not one of those system ports. They were the ports that could be defined by users, and therefore there were some problems with proper operation of NFS protocols for some time. Okay. So there are various issues of this kind, including some small, slightly more simpler issues like the file size limit being 4 GB, etc. Okay. So, but NFSv2 solved one important problem, that of giving access to files in a local area network quite well, and so it became very popular in departmental setting, where you had to use data from multiple big servers, and so it became very useful, but there was certainly need scope for improving the way it performed, or the kind of services it provided. So after NFSv2, the v3 came into picture about almost I think almost a decade later, and so basically here you try to be slightly better with respect to cache consistency. Let us look at the kind of thing that we can do here. Okay. So notice that in the case of NFSv2, you have if you cache some attributes, you don't look at if anything has changed because of other accesses by other client or server. You only look at it if the attributes time out. Okay. So the timeout essentially defines your consistency window. Whereas in the case of NFSv3, what you can do is, whenever a request to NFS3 modifies a file, you basically the server sends both the attributes that existed before and the ones that you are asking it to change it to. Okay. Now, if the pre-attribute matches that of the client, what the client had already cached, then you know that the data is valid in the client cache. Okay, and then you can update the attributes of the cache data. Okay, that you can do. Okay? Basically, because you now have an elementary check by which you can check it out. Okay. Now the only issue is that the client verifies only on open or when cached attributes time out. So we still have the same as NFSv2. That is, if somebody has changed in between, I can't figure out. Okay. But slightly better because if it turns out that the pre-attribute does not match that of the post-attribute, I know somebody has changed it, and I can probably run some other resolution protocol on top of this. Again, not part of NFSv3, but I can still do it. Okay, it's possible. Okay. Now the other issue with NFSv2 was the fact that your writes had to be synchronous. Now to take care of this, they introduced something called asynchronous writes into NFSv3. Basically, the idea here is that when somebody writes to a server, the server can cache it and keep it in its cache. It doesn't have to send it to disk in its storage system, and it's only required to do it if the client says, now please commit it. When it is requested that it commit it, then the server has to commit it to disk, and there will be latency at that point in time. But then it is guaranteed by, there's a guarantee for the client that the data will not be lost. Okay. And basically this particular model, now you can do the following. A client can write to the server, but it will keep a cached copy of the data, and then it can keep writing. At the time when it wants to be sure that it is actually on stable storage, it can say commit. Once it gets a response, a successful response from the server, it knows that it has been committed to stable storage on the server side, then it can discard its own cached copy. Okay. So till that point of time when it gets the successful response, it has to keep whatever it has written in its local client cache. So by this means, what can happen is that you can ensure that you can write at much, you can support higher IO operations than is possible with NFSv2. Other thing what we can do is, when any process does when you do a close, basically there is you can do what is called, you can synchronize the data of the server, so that there's some kind of blocking operation that takes place, so that whatever data that you have on your system actually can be synced to the server. The other kinds of things that they added was something called a write verifier. What's a write verifier? It is some kind of ID that the machine has. Every time it reboots, it increments that ID. So anytime, that means that it keeps track of the number of times that machine has rebooted, okay, in some sense. So what the NFSv3 guarantees is that server will not discard uncommitted data without rebooting. Either it has rebooted or it has kept the data until it has got a commit. Okay. Until it is told to commit, it can keep it, and only way it cannot do that is if it has rebooted, and the client can figure out that it is rebooted because the write verifier has changed. Okay. So in a sense, the client now has some additional information. That is, I asked you to write something, and if it so happens that it is rebooted, the client can figure out that it's rebooted. Okay. So there is some kind of elementary guarantee that's available. Okay. So there are other additional enhancements, but basically NFSv3 didn't change too much. It has basically tried to make things a bit more efficient. Okay. So for example, one example in that category is read director plus. Okay. In NFSv2, read directory only lists the files. So for example, if I want to do ls minus l, it has to first do a read directory, it will get a list of files, and for each file it has to go and say get me the attributes of each file. Okay. So this can introduce lots of back and forth requests and responses. Again, it can saturate the network. So the idea here was to avoid this lot of chatter between server and client. Idea was to produce something called read directory plus, which actually, in addition to providing the files, it also provides you some of the attributes of each of the files, so that common operations like ls minus l can be handled more effectively. So there is also other extensions like exclusive mode create request. Again, as I mentioned before, you cannot provide atomic operations in the case of NFSv2, because each request can span multiple network requests, and therefore it's possible that the kind of atomicity you are looking for may not be possible. For example, in POSIX, there are certain exclusive mode create models of available, and the idea is to see if you can do it also in the case of in the network environment with NFSv3. So there is an additional models that are there. Okay. So there are various additional enhancements that were made, but fundamentally the model is still the same as NFSv2. So this was the situation for quite some time, and once Windows systems became very dominant, there was some need to support the models of the Microsoft Windows systems, and basically at this time there was substantial modifications that was undertaken with NFS, and this NFS Before essentially is a reworked model of NFS, taking into account two main issues. One is that of making sure that there is better consistency management, one, making it closer to the kind of models that is there in the Windows world, so that both Unix and Windows systems can be clients, and also provide better security models. So there are various aspects that have been made, and fundamentally the one major thing that has taken place in NFS Before is to go for what you might call a stateful protocol. This is quite different from what is there in NFSv2 and v3. And again, if you look at the Windows systems also, they also had a more stateful protocol, and so once NFS Before went to a more stateful protocol, it is possible to support the Windows kind of semantics. Okay. And for the same reason, it's also much more complex. The only plus point is that this re-engineering was done in the late 90s, by which time a lot of experience with networking had already been accumulated. So it was easier to design a much better system than was available previously. Okay. So as I mentioned before, the most important change is stateful protocol. Okay. For example, it has got something called an open call. Notice that in the case of NFSv2, there is no open system call. There's no open protocol. There's no open protocol message. It's not there. Okay. The standard thing is to do a lookup, and then you have to get what you do there is you do a lookup on a string that represents the file name, and then you get a file handle. Okay. And using the file handle, you proceed. Okay. And there is no such thing as an open call. Okay. Here, what you do is you have open, and this is where everything is taken care of with respect to lookup, creation, and what is called share semantics. I'll come to that soon. Okay. Basically, in Windows, you have the notion of a share. Okay. A share is basically a way in which you can say that I am accessing a file, and I don't want anybody else to be able to look at it till I am done. Okay. So I can essentially have a per process lock. Okay. And till that particular system is alive, till that particular process alive, it has got exclusive control over what happens to that particular file. Because this is something which is there in the Windows world, and that's what we call the share semantics, and that is what they have also incorporated here. Okay. Similarly, close. Okay. You can, if you have accumulated a lot of state, okay, you can ensure that you release the state through various flushing mechanisms, so that the state that is across the servers and clients, etc., they are somehow made more, let us say, harmonized. Okay. So again, what are the various models? We can have locking at the file level, we can do it at the process level, or you can do it at the client level. So there are three models that are available in NFS Before. So locking is the regular locking that Unix also provides, which is basically at the file level. Okay. That means that I can have a file open for read, and nobody else will, if I lock it in the read mode, nobody else will be able to write it. I can, at the same time I can allow multiple parties to read it. Whereas if I lock it in the write mode, I am only the party which locked it in the write mode only has exclusive access, and nobody else can write it. Okay. Similarly, in the case of, I already mentioned about shares, about delegation, basically it turns out that oftentimes a client can take responsibility for a particular file and completely, and that means that it manages all aspects relating to that particular file. So the idea basically is that a server can be supporting multiple different activities, and these activities could be most likely disjoint. If they are disjoint, then it doesn't matter, okay, if multiple clients are accessing this particular file server. All that we have to ensure is that somehow each client access only a portion of that particular files exported by the server, and if that is done, then it is sort of delegated. You might say each of those particular files, each of those clients which need that, then it's possible that the client doesn't have to send any network messages to with respect to consistency. Okay. So certain groups of files can be managed by one client, they are writing or reading whatever, other parties don't even want to look at it. So if I have a delegation for that portion of the file system, they essentially don't have to actually, they don't have to, that client doesn't have to send any messages to the server to check if somebody has modified it or not. That's basically delegation. Okay. So these things also have been provided, and for providing these things, locking, shares and delegation, you need to have a stateful protocol. Okay. The server has to keep track of the state. There is some state that is kept by the client as in the previous cases NFSv2 and v3, but there is now state that this NFSv4 also has to keep track of, especially what all delegations have been done, what shares are existing, in addition to what blocks have been taken by various clients. Okay. So all these three things have to be done, and there has to be, because of the state that has been accumulated, it turns out that if there is a failure, there can be failures for multiple reasons. There can be failures because of client crashing, or the client crashing, server crashing, or there could be network partitions. Because of all three possibilities, the stateful protocol is going to be complicated. You essentially have to figure out how to manage the recovery process when some of these things happen. Okay. So there is a lot of complexity, and if you look at the specification of NFSv4, it's quite long, and it discusses all these issues, what happens when the server dies, when the client dies, whatnot. Okay. Other thing that has to be done, so that has been done in the case of NFSv4, is that it gives a single view of all exported file systems. Essentially, it provides to each client a single view of all the things that it can access. Okay. In addition, many times what happens is that you have on a server, you want certain parts of the file system to be exported. For example, you may be interested in looking at /a/b, and you also might be interested in /a/b/c and /d. Now, I want only access to /a/b or /a/b/c/d. Okay. Now, in previous cases, in the previous NFS versions, you need to have two mounts, and both these mounts had to be handled separately. Here it turns out that because of the single view, okay, it turns out that you can have a uniform view of what the server is exporting, and it also, when you're doing the path traversal, it turns out, it figures out that you are going through, for example, some intermediate nodes which are not really supposed to be seen by the client. So all those things are done by NFSv4. Okay. The other aspect that NFSv4 does is integration of mount and locking protocols. As we discussed before, it turns out that NFSv2 has to interact with other infrastructure like Portmapper, mountd, lockd, statd, and they were complicated for multiple reasons. there could be security holes in each of these programs. That's one possibility. So that means that there could be different models of security in each of these programs because they are different programs. Okay. So there could be firewall issues, and so various issues of this kind kept cropping up again and again. So finally, NFSv4 decided anyway we are going for a stateful model, and we have to make sure that we have to interoperate between multiple systems which might have different models of security, etc. in order to have some uniform way of handling this, and therefore they eliminated all these things. And for example, in NFS Before, there is a port number 2049 which is fixed for NFS Before, okay, and it is only TCP. There is no UDP here, okay, and because there is no UDP, some of the issues with respect to UDP storms and other things have gone away. Okay. So essentially TCP, as we have discussed before, has some congestion mechanisms, congestion avoidance mechanisms, and therefore it is a slightly more stable protocol. And because it is using TCP, now NFS Before can now be used across internet, okay, in case it is feasible. Okay. And the reason why, of course, it has become feasible is because they are much more efficient implementation of TCP nowadays compared to what was there in the early 1980s. And so TCP is no longer considered a heavy protocol. It has been optimized fairly well. So its performance is not any inferior to UDP protocols nowadays, even though it does quite a bit more like congestion avoidance. So let's look at some of the major changes that have taken place in NFS Before. Okay. First of all, it has got something called a compound procedure. If you look at NFSv2, it dealt with RPC, okay, remote procedure calls. It had to be one RPC at a time. So if you wanted to make some complex atomic change on the file system, you had to send multiple RPCs, and because there are multiple RPCs, one could not be sure that actually it could be done atomically, because it is sent across multiple interactions. Okay. So this was changed in NFSv4 so that you have what is called a compound procedure, so that you can now provide all the operations in one single package in some sense and send it across. And it's the business of the server to ensure that all these things are done, if possible, atomically. Okay. Now it is essentially, the ball is now in the server's court. It's not a lot of interaction between client and server for specifying multiple operations. Of course, this introduces some complexities. The question is that of error handling. Previously, in the case of RPC, if you send some request, you will get some response saying whether that part of it succeeded or not, and you have to figure out what to do with it. Here now what's happening is that you have multiple operations being sent out, and so you need to get some idea about where you failed. For example, you have 10 operations and you failed on the third one. You need to be able to tell very clearly that I did first 2 of them, I was somewhere in the midway, third somewhere, I died here, whatever. Okay. I have to give some additional information so that if in case the client had to be in the picture, it had to get exact information so that some clear error handling could be attempted. Okay. So that means that this part of it has become much more complex. The other aspects which have changed also. Let us look at lookup semantics. One problem with NFSv2 was that it when you traverse the file system, once you get a file handle, you have to do it one component at a time. For example, if I wanted /a/b/c/d, I first get a file handle for slash, then I look up a, then I look up b, then I look up c. And if it is, then basically it means that I have 4 or 5 round trips, and that means you have a lot of latency involved. So this one in NFSv4, they made it multi-component, okay, so that you can send a lookup for /abcd, and it will give you the file handle corresponding to that in one shot. Okay. So these are some of the simpler changes that have been made. Okay. Again, as I mentioned before, you can also traverse across multiple file systems. Basically, the client has a notion about various file systems it has mounted. It can actually mount multiple different file systems, okay, and they could all be on the same server. And then as you are traversing it, if you are traversing between one file system to another file system, because they incorporate something called a file system ID in some of the data structures, it turns out you can figure out that you are traversing different file systems, and NFSv4 can actually track all these changes, and it can provide the right semantics with respect to lookup. Okay. There are some other issues with respect to semantics. In the case of redirected semantics, as I mentioned earlier, in NFSv2, you have to get each file and ask for the attributes of each file one at a time. In NFSv3, we made redirectory plus. In NFSv4, essentially it is the same as NFSv3, except that because of UDP operation, where you have to send a lot of information. For example, if you take a very large directory, if you do ls minus l on it, it can have huge amounts of data that is coming out of it. So with UDP, sending such huge amounts of data can create some difficult situations. So NFSv4 essentially has modified redirect semantics so that we can say how much data actually you can send. Essentially some kind of flow control at the protocol level. Okay. So that's something also has to do. So you can see there are various changes in the NFSv4. So it's a fairly substantial change from the previous models of NFSv3. Okay. In addition, you have something called named attributes. That is, you can, because you are interoperating with multiple different types of systems, Unix systems, Windows systems, and other systems, you can discover what kind of attributes are present. And so there is the idea here is to be able to at runtime figure out the kind of objects that are there and use that to decide how to interact with the NFS server. So for that, they have a procedure called open attribute procedure, by which you can get attributes and file a directory. You can get the directory and then use that information to figure out what to do with it. Okay. Certain things may be available, some things may not be available. Okay. Similarly, because now the scale of the systems is becoming larger and larger, they wanted to support things like file system migration and replication. Okay. So sometimes a file system is available in a particular place, and the system administrator can move it to some other place, either for temporarily or for permanently for reasons of efficiency or management, etc. Now, if you have written an application and it has certain model of where the data is present, it's not a very good idea, but suppose it has such a model, then there is a subsidiary protocol in NFSv4 by which you can figure out where the locations, there is something called FS locations, and this file attribute will tell you where exactly the location of the file system is, and then use that to actually make the right kind of accesses. Same thing with replication. It's possible for you to come up with some way in which you can distribute the load also, okay, based on this kind of model, okay, this kind of information. As I mentioned earlier, one of the major changes in NFSv4 has been better cache consistency models, but it's more complex. For example, you still have the same model that was there in NFSv3. For example, you can, as I mentioned before, both pre-attribute and post-attribute file can be are sent to the client, and you can check whether the data is still considered. So this is still there in NFSv4. Okay. But because you have models like delegation, you are guaranteed that certain things cannot be changed without your knowledge. Okay. You basically get exclusive access to something. The only way you can fall apart is in case you have crashes in the system, especially when you have network partitions. So this is a big issue that we are going to look at from soon. Okay. Basically, our issue is that for cache consistency, if network partitions take place, then not much can be guaranteed. So one thing that NFSv4 does to make sure that things are slightly more reasonable is that it tries to be write through as far as possible. Okay. So in the NFSv2 essentially is write back. The caching is always write back. That means that you can keep some information about what you have changed, not reveal it to anybody till some other major, till something interesting happens. Okay. Whereas in the case of NFSv4, some parts of it, of the system, are made right through, so that you can, as things are changing, you can get some information. For example, if you have a delegation, that means that of a particular file, and you are writing it. So here what you do is, you keep on sending some information like attribute information to the server. For example, you could be sending that I am changing the size of the file. Okay. So some parts of it can be made available to the server, so that the other parties can actually find out that some changes are taking place. So in some places write-through is used. If you think about it carefully, you will see that there are too many issues now trying to be handled in NFSv4. There are some things which are like NFSv3 when it comes to pre-attribute and post-attribute. There are some models where there is write-through is being attempted. There are issues with respect to partitions which are also expected to be handled. So there are many things that are coming in, and it turns out that integrating all this is non-trivial. So the model is very complex, and so that means that somehow we need to figure out a better systematic way of understanding why cache consistency or consistency models are not so easy to engineer in a system with networks, okay, which is what we will look at soon. Again, how does NFS Before data structures look like? Basically, you have file system identifiers. It basically identifies the kinds of file systems that are being exported, and you also have a file handle just like in NFSv2 and v3. Okay. I think as was discussed earlier, in a POSIX you have file descriptors. In NFS we have file handles. Now in the NFSv2 and v3, file handles were persistent. That means that once if somebody gives a file handle, the server is bound to respect that file handle. Anytime anybody provides it 1 million years later, they are supposed to produce the data, okay, which is a bit of a, let us say, too much to expect. So finally, NFS Before has decided that it's no point in having the fiction that the file handle is, it has to be permanent and data has to be served permanently. So they have come up with something called volatile file handle. So it helps servers which do not want to provide permanent file handle. This could also be a security issue. For example, I give some access to a particular file for some time, and if I make it volatile, it is guaranteed that I can drop it without, because something has changed. I don't have to honor a particular file handle that has been produced to me, that is given to me again. Okay. So that's one small change. It also has got something called a root file handle. Basically, NFSv4 has a notion of a current file handle. So whenever it is doing any file traversals, it always does it with respect to a current file handle. Okay. And again, this is possible because NFSv4 is stateful, so it can keep track of something called current file handle. Okay. So the way you start in NFSv4, in the previous case NFSv2 and v3, you had to use a mount protocol, Mount-D protocol, to get a file handle. Okay. You basically send a string of a file name, send it to lookup, and then finally you get the file handle. Here what you can do is you can start with the root file handle. So you can essentially say put root file handle, and then it basically gives you the file handle of the server into some buffer that you have specified, and that essentially gives you the root file handle. Using that, you can traverse the file system using lookup calls, and then you can save that file handle. You can also, once you have saved it someplace, you can get it back. Again, all this is because it's a stateful model. All this can be done on the server. Okay. Save file handle, restore file handle, all these things are possible right now. Okay. To ensure that you can do server and client crash recovery, there is a notion of a set client ID. Okay. So now, what is this? It means that different clients will have different client IDs. Not only based on the machine, it also can be based on the specific reincarnation of the particular client. What it means is that the client also can live and die. Okay. So every time it comes up, it keeps track of which version of the client, which life of the client we are talking about. Okay. So that it can discriminate between different lives of the client. Okay. So if the client dies and comes up, it will have a different client ID. Okay. So that you can discriminate between various types of information per client. Okay. Similarly, for locking state, you keep track of the client information, okay, so that if you have to do any recovery, it's possible for me to figure out who has the current information, who doesn't have the current information, update appropriately. So again, all these things you can see is because now we move to a very stateful model, and so it is going to be slightly more complex. Okay. One major thing that NFS Before has done is using what is called leases. What is a lease? A lease is a way of saying that you have permission to use this particular file exclusively for some amount of time. Okay. It can be through a delegation lease, or it could be through other kinds of models of sharing. Okay. And the idea here is that if, for example, the client dies, okay, then at the end of the lease, the server is free to take back, essentially takes back the lease and give it to anybody else. Okay. So the recovery operations becomes very simpler. But this also means that there has to be, because it's now based on time, there has to be clock synchronization as an important part of the system. Okay. Without clock synchronization, it doesn't work. Now we know that clock synchronization is a complicated procedure, okay, and typically you do not get very high accuracy in terms of clock synchronization. It's usually few hundreds of milliseconds. Therefore, there could be still a big consistency window even if you use the semantics. Okay. As I mentioned earlier that you have locking at various levels. You have the Unix-like locking where you do it per operation, or you can do it at the level of per process, like what Windows has, CIFS, like shares reservations, or you can have it at the client level, the delegations I mentioned before, okay, which we'll talk about next. Okay. So basically in delegations, you are allowing a particular client to manage a file. Okay. So for example, let's take the case of locking. There could be multiple processes in the particular client, and once a file is delegated to that client, any process on that client, it doesn't have to go through the server. So in a sense, it reduces the amount of network traffic that is there. Okay. Similarly, when there is a question of closing, let us say the file, okay, there's no need to talk to the server. Okay. You actually talk locally to the client implementation of NFS Before, and only when the delegation is taken off, then you have to flush all the dirty data to the server. Okay. Now there are some issues here. Basically, if when I'm trying to delegate, etc., you can also take back the delegation. For example, one client requires something to modify some files, and some other client also can come and say it wants the file. It's possible for you to get back or call back the delegation, but it's very critical now that the network is not partitioned. So there are various, in all these operations, anytime what happens is that before a delegation is given, you first check whether your firewalls and other things allow you to do a callback. You need to check all these things. Basically, you can, sometimes there are asymmetric access patterns. You can send out but may not be able to receive it. Okay. So because of the reasons, delegations, etc., are carefully defined, so that the very first thing that you do in a delegation is to check whether you can do a callback. Okay. If you cannot do a callback, then the delegation is not allowed to happen. Okay. So there are a lot of interesting things that happen in delegation, mostly because partitions, firewalls, all those things also can create some complications, and these things are defined in the standard in some detail. Okay. Okay. So as I mentioned earlier, you have this revocations possible via callbacks. Okay. And the most important thing about NFS Before is that it has what is called close to open consistency. That means if you have a delegation and only when you close it do other people see the modifications you have made. Okay. This is similar to what is there in the Windows world. This is what is called close to open consistency, and this is what is provided in NFS Before. Okay. So this is the only thing that you can assume. So the model of consistency in NFS Before is slightly complex. It's got too many let us say, ways of handling it, and therefore you have to be very careful when you start using NFS before. It's better mostly, but you have to know the details. Again, with respect to security, they have made it much tighter and better. So one is Kerberos, which is also there in, I think, in NFSv3, but they provided another model which is called Lec-10, and this is similar to your SSL model. I think SSL, I think most of us are familiar with. Basically, here you have the server has a certificate, but the client doesn't have certificates, and the clients authenticate themselves through username and password, because usually clients don't have certificates. So NFSv4 also has provided something similar. So it's based on a model like SSL, okay, so that you can, when you want to access it, you can give name and password, and that allows you access into the system. Okay. There's also some other types of models by which you can negotiate authentication, integrity, and privacy parameters. There is some particular aspects of the protocol. The access control is closer to the Windows NT model. This access control is model. Notice this is somewhat different from Unix. Unix has this RWX model. Okay. Basically, we have only categorized as 3 parts: user, group, and others. This one is slightly more elaborate, and so this is a model that has been adopted. Okay. Again, there's some minor additional things like string UIDs and DIDs. Okay, I'll briefly mention the CIFS protocol. I'll just highlight some of the important aspects. This is an asynchronous operations, just similar to what is there in what we discussed now, NFS Before. It has got command batching just like the compound operations, and it has got, let us say, some of the similar services in NFS Before, and so it provides things like file access, locking, and caching aspects. They are similar to what is now there in NFSv4, and I'm not going to go into too much detail about these things. Okay. And they also have similar ideas about performance enhancements, read ahead and read right behind. And when it comes to sharing files also, there are the locks, are multiple types of locks are there, and similar to what is there in NFSv4 also, you can handle file system replication and load balancing. The security model is based something very what is there in Windows NT, something called domains, and it also has some authentication schemes, like for example challenge response models, and again I'm not going to go too much in detail here. So when you integrate Windows and Unix, there are a lot of issues. There are a lot of issues with respect to access control mechanisms and consistency management, file locking semantics, etc. But if you look at NFS Before, most of these things have been harmonized to quite a bit extent. Okay. So now the integration between Unix and Windows is much better. When it was with NFSv3 and CIFS, it was very difficult. Before has actually done quite a bit of managing this discrepancy between the two systems, and so now it is easy now. If you support NFS Before, essentially support both CIFS clients as well as Unix clients without too much difficulty. Okay. So I think I'd like to conclude today by saying that NFS is a much simpler model than if you were to go for a cluster file system, which is basically saying give me POSIX semantics across all the nodes. This turns out to be a very hard problem, and NFS started as a crude approximation to this POSIX model, and it has become slightly more better and better. But there is inherent complexity and difficulty of providing a cluster file system model over unreliable systems, either networks or machines. Okay. This is a thing which is a big issue that we want to study later. Okay. From next class onwards, we will start looking at why this issue of giving let us say, a proper semantics in a distributed system is so difficult. Okay. We will look at that part. And again, the one important thing I want to stress again is that if you are using NFS, be clear about the consistency model that you are using. Okay. This can be a surprise, and oftentimes many people are surprised by getting what is called a stale file handle, because they don't know exactly how systems are behaving with respect to deletions or modifications by other parties other than the user. Okay. So again, we'll in the next class we will start looking at issues relating to distributed systems and consistency models.